Hello guys, welcome to my YouTube channel. In this video, I'm going to explain the working of distributed generation. So I'm not going to focus on theory. My main focus is to explain the load flow analysis. In this video tutorial, you will learn load flow analysis for a distribution network. I have a reference paper. I will took formulas, objective function from that paper, and then I will implement that formula into my distribution feeder. I will explain through paperwork, and then I will implement it to the Matlab program. This Matlab program I will attach in the description. You can use it. Also, I have a reference paper you can see here. Here you can see it's electric power and energy systems. So let me show you the network figure. Here you can see the author has took this distribution filter as a reference. Here let me explain a few things. Here you can see all the things here. So we have same technique, but we have a different distribution network. So let me show on which network we are going to work. So here is our distribution network that is different from the reference work, but I will took the objective function from the reference paper. Let me open this in the paint. If you see in the next paper, here you can see this is the next figure. So to make this case simpler and easier, the author have done a technique that he makes circle just like it. This is the distribution network we are going to use, and this image was created before. Now I am going to explain. First of all, we have to do the sum up these nodes. We have to sum up these nodes, and then we have to make a single node. And in next step, here you can see that, let me explain one thing. Here is the 25. So that 25 means 25 kVA. We have 1 2, we have node 1, we have node 2, we have node 3. At node 3 we have 25 kVA load. Here R represent rapid conductor, and here we have G, we have dog. Conductor types, we have O, and we have G. So, and also we have U. These are all conductor types. I will explain these conductor types in a while. So all the triangles that are mentioned here represent load type. So at 36 we have 100 kVA load type. Anyway, we are going to focus on main point. So this is considered as node 1, just like it. So in this figure, that all the load between it, what he done, So we are going to sum up all the load that is between the red circle. Here is 200 kVA, 100 kVA, 25 kVA, 50 kVA. We have sum up all the loads inside this circle, and then we are going to name it as node 1. And in next step we have to calculate the node current, which I will explain just a moment later. So for next node we are going to sum up these loads: 10, 11, 12, 13, 14, 15, 16, 16, 17, and 18, and all these. In next node we are going to consider all these. Here is 1, here is 2, and in so on we have 40 nodes. Let me, to save our time, 3, 4, and 5, 6, so 7. Let me show the Matlab programming that I have created. Let me run it. So when I'm going to run it, it is asking for a value. If you press 0, it means the program will load the data that I have already have stored in it. So if you want to change the data, if you have a different network, then you can press 1 and it will ask all the values. Just a moment, let me press 1. Then it will ask for number of nodes and total load, each and everything it will ask, and at the end it will run the program. So let me run the program by default values. So when I will run it again, let me press 0, and just a moment, let me click over here. So when I click on the run button, when I have put 0 and enter, here I am, my program is stopped. So here is all the reference values is stored. So here you can see that in my load array, let me open this variable. So all the my load data that I have entered is stored in this variable, dg variable. So here you can see in this dg variable, dg, all the variables that I have stored initially, you can see here, and this is the workspace. So what is the difference here? Workspace means all the values that are executed up to this point, okay, 69 point are shown here, and these are the values on left side. These are stored in the dg variable. So let me check the load array. So let me double click it. So now you can see here load array. So here we have total nodes. We have 40 nodes, and in this paper there are 38 nodes. Our network is bigger than the network that is taken in the paper, so that's why I have selected 40 nodes better for it. If you take into consideration, we have node 1 45 kVA, and at node 2 we have 60 kVA, at 3 we have 50,000 kVA. So let me sum up it. Just focus on command window, sum, and I have to put load underscore a. So let me change now. So here you can see that we have 14,740 kVA. So here you can see one more thing, that is our reference voltage that are we have taken 11,000. We have 40 nodes, and resistance and power losses will be, we will calculate it. Node current and segment current. There are two things: segment current node current. Let me explain in a while. So let's jump on to our clipboard, and up to 3 nodes I will calculate things over there. So welcome back. So I have write all the nodes on a paper, and let me explain in a simpler way. So here we have nodes, node 1, node 2, node 3. Here you can see that at node 1 we have 45 kVA load, at node 2 we have 60 kVA, at node 3 we have 50 kVA. Here you can see this value is stored in our Matlab, and so on. We have 40 nodes. So here you can see that we are going to find the node current. We have to divide our load array by square root of 3 and reference voltages that are 11,000. So let me open the paint. Here you can see that at first point we have 45, and here I have done a mistake. I remove that. In second point we have 60 kVA, in third we have 50 kVA. So here let me show you what it means by a node current. At bus 1 we have a load that is 45 kVA. So this 45 kVA, how much this load will take current, that is node current. At, let me explain again, at bus number 2 we have 60 kVA load, and how much this load will take current, that is node current 2. Here I have mentioned, and here I have mentioned node current 3, that is 50 kVA. So in Matlab program here it is done that, and I have, and now in Matlab programming I am at this point, it means I have executed this file. So let me check the node current. Here you can see that node current we have 2.36, we have 3.14, we have 2.62. So let me open the next image. So let me open with it. Okay, so here I have write all the values: 2.63, 3.14, and 2.62, and here you can see that the values are exactly same. So I have explained the node current, and in, let me show you by the reference paper. So here the formula that represent I, that is current, 0 to 1. It means it is talking about. So now I have write more things on my board. I have take a picture and let me explain these things. So here I have done calculation for segment current. Here you can see that I have total load above, and then I have the formula. Here you can see that from the reference formula, that is here SI, that is total. I total means segment current, or you can say that total load current. So kVA total I have summed that up, that is here. So here you can see that 14,007, when I have calculated this formula I have 773.64 ampere that I have right here. So at this point I have 773.64 ampere. So at this point 773.64, it means that so in next point we have 2.36 amperes load, that bus 1 will take 2.36 amperes. So when bus 1 will take from it, then 773 that is coming from the base, that is coming from the grid, and then is subtracted by 2.36, then we have 771.28. So that we can see that I12, and we say it segment current, and this segment current will comes at number 2, and this segment current 770.28, and then we have to subtract this 3.14, and then we have a segment current that is actually 768.1383. So at 1 we have this value, sorry, at 1 we have this value, at 2 we have this value, and at 3 we have this value. So let me check in my Matlab program. So here we go. Let me click on the step button. Here is segment current. Let me check. Here I have 773, and this calculation is without DG, so we are not going to subtract the node currents here. So let me click on and click to run to cursor. So when I click on the step button, then here you can see that here it is subtracting the node currents that I already explained and we have calculated in previous step. So here you can see, so in this step here you can see at number 2, and then we have segment voltage drop, and that we will cover in next step. So again, when this for loop starts again, then we have a segment current, and at this point we have how much I double I represent number 3. So segment current number 3 will be segment current 3 minus 1 2. This means 2, because double I is 3 and minus 1 2, and at segment current 2 we are going to subtract its node current as I explained here. At this point number 2 we are going to subtract number 2 node current, and segment current number 2 is 771.28. So let me check again. So 771.28 is number 2, is segment current here, and node current is 3.1492. Just a moment. 3.14 3.14, and segment current is 77. So when I click on the step button, it is calculated for 768 that I have plotted here, and here you can see that that is 768.1383. So let me explain now the next step, that is voltage drop. Here you can see the formula here. So let me explain by the Matlab program. So here we have a segment voltage drop. Here you can see. So that is simple. We have to multiply the segment current with impedance array. So we will get the segment voltage drop for node 1, and for other nodes we have different calculations. So at node 2 we have at this point, at number 2 segment voltage drop, we have impedance array multiplied by segment current. So that is a simple formula. So here you can see in my, here I have again draw these things. Here you can for your understanding, here is the segment current line, here is NC node current, here is our segment current, here is our node current, here is our node current, and here is our segment current. At this point we have segment current. When we will subtract node current, then segment current for next node will be calculated. So here I have draw the figure for segment voltage drop. At this point we have a 773.64 segment current. When we will multiply it with the impedance 1, then we have a segment voltage drop. So at bus number 1 we have node voltages. At bus number 1 we can say the node voltages at V reference. Here you can see in my Matlab program, here is reference voltages that are 11,000. So at this point we have segment we drop. So I refer it as 11,000. So at 11,000 minus segment voltage drop, we have node voltage. So here you can see that we have node voltages that are V reference, and then we have to subtract segment voltage drop, that are due to the node 1. So in next step we have node voltages, and here I have put 1. So if we want to, here is the answer and above is the formula. This is the formula and here is the answer. We are going to find here node voltages for our bus number 2. So we will put the node voltages, I mean node voltages. We have node voltages 1, so we are going to put this node voltages here, and then we will subtract segment voltage drop from number 2. Just like that we have calculated the segment current, and then we are going to minus the node currents. In the similar way we have some node voltages, and then when we will subtract segment voltage drop, then we have next node voltages. Here in Matlab program you can see that we have node voltages, and here we have number 3, here we have 3 minus 1 number 2, and here we have number 3. So it's just like the same, we have calculated the node currents. We have to calculate the power loss, and that is simple, I square R. So let me show on the Matlab program. Here let me click on the cursor, and here you can see segment currents, node currents, and let me show you segment node voltages. Here you can see that in a simpler way I can tell you here that at point 1 we have 46 46 segment voltage drop, and when I going to subtract 11,000 minus 46, then we have 10954, and we have 10954, same value. And in next step when I have to subtract 91, so I will minus 91, so 10863. Here you can see that 10861. So here is the answer, you can see here. So here is our next part. We are going to incorporate DG here. So let me explain here the working of DG. So all the part that we have done above is without DG. So here below we have a process with DG. So let me explain. Here is the load current for DG1, and here is a load current for DG2. You can change it to 0 colon 10. So you can change the value of DG, but it's a simple learning program, so that's why I have put a fixed value. And here also I have put a location of 17 position. Also you can change from 1 to 17. You can in this way it will be put in location from 1 to 17, but I have to create a simple program. Here you can also change its value and also the location for 30. Also you can change from 30 to, if you want to change from 30 to 40, you can put just in a way. Then it will be first DG2 will be implemented at 30, then it will be at 32, then 33, then 34, etc. So let me go in such a way. So what we have to do here, we have to sum up the dg currents, dg1 and dg2. Here you can see that we have total, just a moment, we have node current here, and segment current we have 773. So first we have 308 and 7 is to 76. So let me show you. Here you can see that segment current, again same formula that we have. So here we are going to subtract the segment current one. Just a moment, let me show you. Continue. Okay, so segment current, and then we have to subtract the total dg currents, which we are going to, just a moment, sorry. So here you can see that here we have segment current, that is, and when I click on step button, then we have 188. It means in start we have 773, that we have our mainstream, our grid station is at point 1, and our grid station is installed at this point, and then we have to, and then all our current will move in such a way that, in such a way, and then again from this point, and from this point, then to this point, all our power is coming from this point. So if we install a DG at let me blue pen. So initially it was 773, initially it was 773. So if I install a DG here, just for example, for understanding, let me install DG1 here and install DG2 here of 300 value, and here for 200, just for a consideration. So we have 300 plus 200, 500. So 500 current will be supplied from here. So 773 minus 500 is actually equals to 273, just for a understanding. So by this you can understand that why our node current is changed from 773 to 188. And then we have segment current minus node current, we already have done this formula. And then we have segment current, so why j minus 1, j is 17 minus 1, I mean we are going to put dg1 at a 17 position. So let me click on the step button. So let me run to cursor. I have clicked here, run to cursor. Just a moment, all the program is executed. Let me run the program again. Okay. So here you can see that segment current up to 17, up to 17 is 16 is solved. Okay, so there is a question that why the values are minus. So no need to worry about that. That at 17 point. Okay, so at this point we have g equals to 17. It means we have our dg1 is added here. Here you can see that at 17 position we are going to add dg current plus segment current. So dg1 current is added here. So DG implementation is actually addition of currents. So here you can see at point 17. So let me edit it. Okay, click on step, step, and step. So when I click on 17, just a moment. Here you can see that our values is changed from minus to positive. It means we have integrated DG here. It means at this point we have uh, added our current here, and then this current will be uh, submitted to the load, to the nodes, to the loads. So okay, sorry. So in next point we are going to calculate the segment current minus node current, that is again for j plus 1, and here we have digital implementation. Here we have again node voltages, segment voltage drops. So DG concern is actually related to segment current. Node current is fixed all the time. Segment current will be changed due to the DG implementation. So that's why I have make this sequence separate. Here you can see that. So here you can see that we have segment voltage drop depends upon segment current, and these all formulas are same as we have done earlier. And here there is a portion of DG checker, just ignore that, I will explain a bit later. And then we have power losses, and we have then here is power loss, compare compare and power loss. Here is a simple uh, you can say a simple mechanism to store the best value. So so if power loss, let me show you. Power loss sum, if power loss compare equals to 1, always true, then power loss sum equals to power loss CMP, and then we have store all the values. So this is the technique to store our best value in it. And then we have our Excel sheet program, and then we have, then all the next things are just for, here is we have Excel for, so let me open. So when you will run the program, this Excel sheet will automatically generated. Just a moment. Let me right click and open outside Matlab. Okay, so here you can see that on for a while just ignore this value DG checker. Okay, so on left side of G column we have calculation values without DG, and on the right side of G we have calculation with DG. So here you can see that we have in the start 773, and then we have 771. You can take understanding from this point. Okay, and then we have voltage drop V1 V2. Okay, so when I subtract 11,000 minus 46.952, then I will get this value. And power losses is actually segment current I square, and then you have to multiply, or resistance is not mentioned I have here, but that already is included in the Matlab, that you can see from here, resistance and impedance array. So just a moment. So for voltage drop we will include impedance, and for power loss we will include resistance. So here you can see that at point number 17, we have included our first dg, and at point number 30 we have incorporated our second dg. Hopefully you understand many things. If you have any question in mind, feel free and share. So press the subscribe button, and if you have any requested video, you can ask in the comment. Thanks for watching. See you.